Today, for the first time, I want to shift gears and talk about light or electromagnetic radiation in general, not as a wave, but as a particle. We established from the beginning of this unit that there were 4 properties of waves that were exhibited by EMR, and therefore EMR must be a wave. Diffraction, interference, refraction, polarization. We're not taking that away. We're not wiping that out. Light still is a wave. But we're now going to suggest that light also has a particle nature. We say actually now that light has a wave-particle duality associated with it. It's both a wave and a particle. For the next few days, we're going to talk about light as a particle, and then we'll try to just tie it all together at the end. In 1905, Einstein came up with something called photon theory to explain a phenomenon called the photoelectric effect, which we'll talk about in just a short time here. Nobody could explain that before. The photoelectric effect had been discovered about 20 years earlier. Nobody could explain the observations that were made, except Einstein's photon theory in 1905 did explain the observations that were made. This is what photon theory said. And it built upon, by the way, it built upon this theory that had been around for a short time called quantum theory. Photon theory says, in essence, that light exists as a particle called a photon. A photon is a particle of light, or more technically defined as a quantum of energy, a quantum of electromagnetic energy. So we're now saying that light exists as a wave, like we have been since the beginning of this unit, but we're saying as well that light exists as a particle, like a rock, like a stone. Okay, if you have a beam of light, that it is a wave, but it's also this stream of rocks that are being thrown. That's pretty hard to visualize, right? How can it be both? Well, we can't really visualize the wave-particle duality of it because it's outside of our realm of experience. What I want you to understand is that light is not this with particles moving along a wave. That's not what we're talking about here. Okay, we're talking about its very nature. It is a wave, and we now know that it is a particle, which, good luck trying to picture in your mind what that looks like. I can't. Okay, so if you can't, that's okay. It's pretty difficult to picture something that we've never actually seen before. How do we know that it does have a wave-particle nature, a wave-particle duality associated? Well, we have evidence. So there's observations that support the wave nature of it, refraction, diffraction, interference, polarization. There's also observations that support the particle nature of it. And we'll talk about what some of those observations are over the next couple of days. So, bottom line is, light, in addition to being a wave, is also a particle called a photon. And a photon, more technically described or defined as a quantum of energy. Now, we have an equation that describes the amount of energy that a photon of light has. And that equation looks like this. E is equal to h times f. Or, because f is equal to v over lambda, what's another symbol for v, by the way, when we're talking about light? C, right? We could replace that and say E is equal to h times c over lambda, replacing f with v over lambda or c over lambda. The energy of a single photon of light, the energy of a single particle of light, is hf or hc over lambda. Just like the energy of a pebble, a rock that's being thrown through the air, is 1/2 mv squared, the energy of a photon is hf or hc over lambda. F is the frequency, right? We know what that is. C is the speed of light. It's 3 times 10 to the 8 meters per second. Lambda is the wavelength, which is measured in meters. E is the energy of the photon, of a single photon of EMR. Whoops, what did I do? H is, well, that's new. H is a constant. H is a constant called Planck's constant. And that's named after the guy who first actually come up with this quantum theory, not photon theory. Photon theory is kind of a refinement of quantum theory. A little bit before Einstein, Planck came up with this quantum theory that Einstein kind of took and refined and turned it into photon theory, the idea that light exists as a particle. Planck gets some credit here, though, in that he gets the constant named after him, Planck's constant. The value of Planck's constant is, you can see this on your data sheet, it's 6.63 times 10 to the minus 34 joules seconds. Joules times seconds. But if you look at your data sheet, there's actually two values given. 6.63 times 10 to the minus 34 joule seconds, or 4.14 times 10 to the negative, I believe it's 15. Somebody check that. 10 to the negative 15 EV times seconds. What's an EV? Electron volt seconds, yeah. How can we have two values of one constant? Yeah. Yeah, it's different units, right? It's just different units. What's the speed limit out in the highway? Well, between here and Highway 2, the speed limit is 100 kilometers per hour, right? But if you're an American and you're driving your American car that's got miles per hour on the speedometer as opposed to kilometers per hour like we have, then you're going to think, well, the speed limit's 62 miles per hour, right? What's the difference? 100 kilometers per hour, 62 miles per hour. Are those two different numbers? Well, they kind of are, but they mean exactly the same thing, right? This is your 100 kilometers per hour. This is your 62 miles per hour, represent exactly the same thing. So whichever one you're going to use just depends upon what ends up being convenient with regards to the units you're using elsewhere, like Jake said, with energy. Now, there are times, most times you can use whichever one you want. Most times whatever one's convenient, okay? There are times when only this one is valid. And I'll describe those times for you as we go through. So you'll know when you can use either one and when you could only use joules. But I will say this right now. If throughout this unit you're getting confused as to when you can use joules, when you can use electron volts, you're getting a little bit mixed up, then I would suggest to you always use the top one. The top one can always work. The bottom one will usually work as well if it's convenient to use it, but not always. So if you end up being a little bit confused, just use the top one. It does sometimes mean a little bit extra work, extra unit conversion that you don't really have to do. Okay, but if you're confused, then just do the extra work. You got tons of time, right? Tons of time on your exam and on your test. So just use the top one if in doubt. All right, now you can imagine here, we'll do an example in just a second, but you can imagine here now, remember I said first day of the unit? Okay, Danielle asked a question just a minute ago about this, right? She said, do we have to remember all those frequency ranges? No, you have to remember 3 of the frequency ranges, right? And then just fill in the blanks for the rest. If you're given a wavelength, then use V is equal to F times lambda to find the frequency, and then use the 3 frequency ranges that you memorized. Remember we said the first day, though? If you're given an energy, you're going to learn an equation that would allow you to find the frequency and then compare it against the frequencies that you memorized. This is that equation. If you're given an energy, of course, you're going to say F is equal to E over H, find the frequency, and then compare it against the table that we memorized and determine what kind of EMR that we have. Okay, let's do an example here. This is example number 1 on your sheet that I handed out the first day of the unit. It says, determine the energy of a photon that has a frequency of 5 times 10 to the 14 hertz. Really, really easy, straightforward question here for us. We got an equation. E is equal to H times F. What's the value of H? Depends. What do you want it to be? Well, if I make it 6.63 times 10 to the minus 34 joules seconds, multiply that by the frequency of 5 times 10 to the 14 hertz, I'm going to get an answer of 3.3 times 10 to the negative 19. What would the units for that be? What would the units for this energy be? Joule seconds times hertz gives me Joules. What if I had have used the 4.14 times 10 to the negative 15 electron volt seconds? What do I end up now with? I get 2.1. What would the units be? Electron volts. Which one's correct? They both are. Now, this is a multiple choice question, or a numerical response for that matter. They're going to specify what units, so you have to be prepared to do both. But you don't actually, like I said a minute ago, you can always use joules, right? If they give you an answer in electron volts and you just don't like using that 4.14 value, what should you do? Do it in joules, get an answer in joules, and then convert it to electron volts. That's an extra step, right? But it always works. So if you're uncomfortable with using electron volts in these questions, because there is the odd time when you're not allowed to, this is not one of those times, then just use joules and then convert it at the end if you need to. Next example, number 2, says how many photons of that frequency would it take to obtain a total EMR energy of 2.5 times 10 to the 22 joules? How many photons? How many? What the number of photons? What do you do when you're looking for a number of something? I see a couple of you looking over here at the always do list on the board here. When you're looking for a number, what do you do? The total divided by the amount for 1. We're looking for a number here, right? So it's the total something divided by the something for 1. Let's try the total energy divided by the energy for 1. Makes sense, right? Since we have an energy given to us. The total energy here is 2.5 times 10 to the 22 joules. Okay, what's the energy for 1? What's the energy of 1 photon? Oh, come on, you know this. How about H times F? Right, the energy of 1 photon. What value of H do you want to use here? 6.63 joule seconds or 4.14 electron volt seconds? Joule seconds, right? Since we have an energy in joules, we want to get an energy for 1 photon in joules. So let's use the joule seconds. 6.63 times 10 to the minus 34 joules seconds times 1.00 times 10 to the 16. Now, had you been given this total energy in electron volts, then what would you have done? You could have converted that to joules, or you could have found this energy in joules and then converted to electron volts, or you could have just used the 4.14 value for that and skipped a step there. Okay, we sub those numbers in. We get a value for the energy of 1 photon of 6.63 times 10 to the negative 18 joules. We sub that in here. And we divide the 2, and we get 3.8 times 10 to the positive 39. It's just a number, no units, right? Because joules and joules end up canceling. Just like we solved for the number of electrons back in Unit 2. There was no units, it was just a number of electrons. Same deal here. Except remember then it was total charge divided by the charge of 1. Here it's total energy divided by the energy of 1. But still, if you look over here on our always list, still the total something divided by the something for 1. Okay, I'd like you to take a look now quickly at worksheet number 20. And I'd like you to take a look at just the first 2 questions for now. Worksheet number 20, questions 1 and 2, please.